Now we're going to look at mass to mass stoichiometry. So we're going to have to remember how to calculate molar mass. Now, remember what stoichiometry is? Stoichiometry is the use of a mole ratio, which comes from the balanced chemical equation, to solve for an amount of a chemical when you are given an amount of a different chemical. So mole-to-mole stoichiometry is a one-step process. You multiply the given chemical by the mole ratio to get the desired chemical. Practice this. Do not be deceived by how easy it is. You must become super familiar with this process before you can move on to mass-to-mass stoichiometry. So let's look at mass-to-mass stoichiometry. We know that a mole is a number, 6.022 times 10 to the 23. This is important because balanced chemical equations are about a certain number of molecules reacting. However, how do we measure a mole in the lab? We certainly can't count atoms or molecules. The mole is a number, however, that number can be related to mass by molar mass. So, as I said, we cannot count atoms or molecules, but we absolutely can measure the mass of a chemical, and you've already measured the mass of chemicals in lab. So in the lab, we can convert from mass, which is easily measured, to moles by dividing by the molar mass. So as we're looking at stoichiometry problems that are mass to mass, what that means for you is extra steps. You're going to have to calculate the molar mass of the given chemical and the molar mass of the desired chemical. And we'll look at the actual the actual steps, but you will be dividing the given chemical by the molar mass to get moles, and then you will be multiplying the desired chemical by its molar mass to get back to mass. Mole ratio is still the key. The mole ratio is the central part of any stoichiometric calculation, and before we can use the mole ratio, the given chemical has to be converted to moles. So let's just jump in and look at an example. If 125 grams of pentane, C5H12, is combusted, what mass of carbon dioxide, CO2, is formed? So here's our balanced chemical equation, which we must have, and we're going to clearly write what we're given, 125 grams of C5H12, and what we want, grams of CO2. So I notice that this is stoichiometry because I'm given an amount of C5H12 and I'm trying to find an amount of a different chemical, CO2. So I know I'm going to have to use my mole ratio. But because I'm given mass and I want mass, I also know I'm going to have to calculate the molar mass of both pentane, which is given, and carbon dioxide, which is what I want to get to. So I'm going to organize my problem by first writing my balanced chemical equation at the top of my page so I can easily refer to it. Clearly state what information I'm given, which is the mass of C5H12, and what I'm solving for. Then I'm going to take the time to write down the conversion factors. First, I know I need a mole ratio. My mole ratio always has the moles of the chemical that I'm given, which is C5H12, with the stoichiometric coefficient from the balanced chemical equation. So in this balanced chemical equation, C5H12 has a coefficient of 1. And then the chemical that I'm trying to get to, CO2, goes in my numerator. So moles of CO2 and 5 moles, where that 5 comes from the balanced chemical equation. So I know I need a mole ratio, so I go ahead and write that down. Then, because it's mass to mass stoichiometry, I know that I need to calculate the molar mass of my given chemical and my desired chemical. So remember, the molar mass has nothing to do with the balanced chemical equation. A mole of a chemical always has the same mass regardless of how an equation is balanced. So when you're calculating the molar mass, it will always be 1 mole of that chemical. Always, 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 always. So 1 mole of CO2 has nothing to do with the fact that there's a 5 in the balanced chemical equation. To calculate the molar mass of CO2, I look at the chemical formula, which tells me I have 1 carbon and 2 oxygen. Then I look at a periodic table. Oops, I didn't mean to do that. I look at a periodic table and I see that carbon has a molar mass of 12.01 grams. I'm going to round to the nearest hundredth. And oxygen, if I round to the nearest hundredth, has a molar mass of 16 grams. So, going back to my calculation, which is right there. Alright, so I multiply 1 by 12.01 grams to get 12.01 grams, 2 times 16 to get 32, and when I sum those masses, I get that 1 mole of carbon dioxide is 44.01 grams. That's its molar mass. Then I have to calculate the molar mass of pentane. So I look at the formula, I see there are 5 carbons and 12 hydrogens. And on this periodic table, right here, you see that carbon has a molar mass of 12.01, and then hydrogen has a molar mass of 1.008, which I will round to 1.01, as I like to round to the nearest hundredth for simplicity. So when I multiply 12.01 by 5, I get 60.05 grams, and 12 multiplied by 1.01, I get 12.12, and when I sum those, I get a molar mass of pentane of 72.17 grams. Now, I'm about to do my molar mass, and I'm not about to do my molar mass, I'm about to do my railroad math. And before we do our railroad math, we always want to make sure we have 2 of every unit, including the given and the wanted. So I have grams of pentane, grams of pentane, grams of carbon dioxide, grams of carbon dioxide, moles of carbon dioxide, moles of carbon dioxide, moles of pentane, moles of pentane. I have 2 of every unit, which means I'm ready to do my railroad math. So I set up my railroad math, oh, and I made a mistake here, but I set up my railroad math with my given value, 125 grams of C5H12, and so I know that grams of C5H12 has to go in my denominator because I want to cancel those units out. And when I look at all of my conversion factors, there's only one conversion factor that has grams of C5H12 in it. So I make sure that 72.17 grams is in my denominator, and then 1 mole of C5H12 is in my numerator. So my grams of C5H12 cancel out. I have moles of C5H12 in my numerator, so I know that moles of C5H12 have to be in my denominator. And when I look at my conversion factors, when I look at my conversion factors, my mole ratio is the only other conversion factor that has moles of C5H12 in it. So that is my next conversion factor. And then my moles of C5H12 cancel out, and now in the numerator I have moles of CO2. And so the last conversion factor that I haven't used yet is the molar mass of carbon dioxide. So mole of CO2 goes in my denominator and it cancels out. And to get my answer, I multiply 125 by 1, divide by 72.17, hit the equal sign. Multiply by 5, divide by 1, hit the equal sign. Multiply by 44.01, and divided by 1 of course doesn't change that. And then I get 381 grams of carbon dioxide. Since I started with 3 sig figs, my final answer should have 3 sig figs. Now, as we went through this process, you will go through the same process for every mass-to-mass stoichiometry problem you do. You will always start out with the mass of the given chemical, and you will convert that mass to moles by dividing by the molar mass of that given chemical. Then your next step will be using the mole ratio to get from the given chemical to the desired chemical. That will always be the second conversion factor. And then your very last conversion factor will be the molar mass of the desired chemical, and you will multiply by the molar mass. Now if you set up your railroad math so that all the units cancel out, this process will happen no matter what. But this will also give you a sense of context as to what you're doing. Converting mass to moles by dividing by molar mass, get from one chemical to another by using the mole ratio, and then get moles of your desired chemical to mass by multiplying by the molar mass.